This video is going to be looking at the very last topic of A2 chemistry for Edexcel International A-level, and it's going to be looking at the organic techniques that we use in organic synthesis. So it's all about the techniques that we use in order to prepare and purify an organic compound. And we are going to be looking at refluxing, purification by washing, solvent extraction, recrystallization, drying, various different types of distillation, and how we can determine melting and boiling point. And then we'll look at a past paper question at the end. So for organic synthesis, we do have lots of techniques that I just mentioned there, and they're all about the preparation and the purification of compounds. You need to know what each of the techniques are, you need to be able to draw a diagram, and you need to be able to describe each of them. So I'll go through them in this video, but you may also want to try to find some other practical videos where you can physically see the techniques being done. Alternatively, try and see if you can get a chance to do them in the lab at school. But we know that that may not always be possible. So the first thing that we need in order to be able to prepare or purify an organic substance is we may want to heat it under reflux. Now, we've looked at this before. We've been talking about reflux since back at topic 10. And a lot of it is because we need to heat a reaction in order for it to happen at a suitable rate. Remember, we always need to find the balance between kinetics and yield. The biggest problem with that is that our organic compounds are very volatile. Volatile meaning that they will easily evaporate. So whenever they evaporate into a gas, then they're going to escape during heating, and we want to avoid that as much as possible. So we use this reflux condenser, which is this part here, and the reflux condenser has this cold water flowing in at the bottom, and it travels all the way around here, around through the back, and it flows out at the top. And that cold water cools all of this section here in the centre, so that when our vapours travel up, they are then cooled, they're turned back into a liquid, and then they drop back into the reaction vessel. And sometimes we might use anti-bumping granules just to give us nice smooth boiling as well. We use heating under reflux for many different reactions. Probably the one that is most common is turning a primary alcohol into a carboxylic acid. We're going to heat under reflux in order to do that. So another method of purification is simple distillation, and we use simple distillation in order to get a liquid product that has a lower boiling point than everything else in the reaction mixture. Now, for simple distillation, we do need quite a large difference in our boiling point, so we tend to be looking at about 20 to 25 degrees. What we do is we heat our reaction mixture in a flask, and you can see we can check it, of course, using a thermometer. And we have our mixture getting to the point where something is going to boil off, or whichever of our products, and the vapours are going to travel, and they're going to go down through the centre of the condenser. Of course, we know that this is going to be filled with cold water. That is going to cause it to turn back into a liquid, and then it can be collected in a round bottom flask, and we call this the distillate. As it's passing through the condenser and it's cooling down, you can see that we can always be checking the temperature, and as long as the temperature remains steady, we're going to be distilling off the same product. Anytime that we get a change in that temperature, if we get a spike a little bit further up, it means that we're getting a new product that's being distilled. So we would probably want to swap out the round bottom flask so that we're not mixing two organic products together that we maybe wanted to separate. As well as simple distillation, we can also do fractional distillation. So you've seen fractional distillation when you were talking about crude oil. And it's very much the same, where it's trying to heat up a reaction mixture in order to turn it into a vapour and then have it pass through a condenser. But what we do this time is we add in a fractionating column. And this is used when we have boiling points that are similar. And the fractionating column, it tends to be filled with glass beads or broken glass, and those act as surfaces for the vapour to condense onto, And then as more hot vapor passes up through the condenser, then it is re-evaporated. So we get this constant condensing and evaporation happening in the fractionating column, and that allows us to get much better separation. And then eventually it will come up to the top with our vapors and of course pass down our condenser then into our collection flask. The third type of distillation, and this is the one that you probably haven't seen before, is known as steam distillation. And this is used to separate an insoluble liquid from an aqueous solution. Okay, so what we do is we pass the steam into the reaction mixture through this tube here, and it comes down and passes in. As it passes in, it causes the immiscible mixture, so remember immiscible meaning that it's not mixed, it causes it to become agitated and it causes it to boil and start to evaporate, and then it means that we get evaporation happening on the surface of both of the two liquids. And actually the most good thing about this particular type of distillation is this third part here, that by adding in the steam, it allows an insoluble liquid to be removed at a temperature that is much lower than its boiling temperature. So this agitation that is caused by the steam allows the evaporation to occur without us actually having to heat it all the way up to its boiling temperature. We can also extract an organic product from other substances in a mixture using solvent extraction. You met this back in topic 10 when you were looking at using organic solvents such as cyclohexane in order to extract something from an aqueous substance. It just varies depending on what it is that you want to use. The most important part is that the solvent that we use should be immiscible. Okay, we want to be forming layers. So it should be immiscible that the solvent that the product is in, and the desired product should be more soluble in the solvent that we're adding. So for example, if we have a product in water and we want to add something like cyclohexane, these two things are not miscible, so these are going to form our layers, and we want the product that is in the water to prefer to be dissolved into the cyclohexane instead. And that allows us to put it into the cyclohexane and separate the two things, and then we can undergo distillation for that. So how this works is we put the mixture into the separating funnel, and then we add in our chosen solvent, we put a stopper on top, and then we agitate it or we shake it. That allows the mixture to separate into two layers. So you would see something like that. And depending on the density of the two substances, one would obviously float on top of the other. And then we can open the tap and we can drain out the lower layer. And then we allow this line here to come down to the tap. Then we close it. And then we into a different flask. Then we follow the drainage of the upper layer so that we then have our two different solvent layers in two different beakers. And then whichever one we need, we discard the other one, and the one that has our product undergoes distillation to get that exact desired organic product. Now, washing is very much what it sounds like. It is a way that we can remove impurities from both solids and for liquids. Now, if we're using one that you're probably most used to seeing is solids, but we can also wash liquids using this method. So we can carry it out using water, an organic solvent, or even sodium carbonate. It just depends on what organic product you're trying to purify. So if we have excess acid, we would use sodium carbonate to remove that. The solvent that we add, whether it's water or an organic solvent, should dissolve only the impurities that are in our substance. We want to keep as much of our desired substance as possible. Any impure solid is going to be stirred with the solvent, and then we filter it. So the impurities are going to then dissolve into the solvent. And then when we filter it, we are left with our desired product. If we have an impure liquid, we mix it with the solvent, and we do this in a separating funnel like we just talked about, and then again each layer is drained into separate containers, and that allows us to remove those impurities. So if we have a liquid that has, the liquid itself is our desired product, but it has potentially dissolved impurities, if we mix it with another solvent, those impurities should dissolve into the other solvent preferably, and it allows us to just keep our desired organic product. Hopefully that makes sense about washing. If we ever wash anything, then typically we want to dry it, of course, and this technique is quite simply what it sounds like. We can leave an organic solid in a warm place to let it dry, or we can leave it in something called a desiccator. And a desiccator is basically just a big glass jar, and we can put in a suitable drying agent. And the purpose of this is to remove any water from an organic solid or liquid. We typically don't want any water in our organic solid or liquid because it causes an impurity. We don't want it to be there, we want it to be pure. So the best way for us to do this is to use a drying agent such as an anhydrous metal salt, such as calcium chloride or silica gel, and that allows it to absorb the water as water of crystallization. And then depending on whether you have a solid or if you have a liquid organic substance, you can remove the drying agent either by decanting, which is just careful pouring, or you can filter it and get rid of the drying agent that way. So this is just a diagram of a desiccator here, and we have our drying agent here that is going to absorb the water. So sometimes what we might also do is we may undergo a process called recrystallization, and they love to ask about recrystallization in an exam. And it goes hand in hand with a process called filtration as well. And we use potentially two different types of funnel that you may not have seen before, and they're called a Buchner funnel or a Hirsch funnel. And the difference between these and the two different funnel and the different types of filtration methods that you've met is that these are attached to a vacuum pump. So there is actually a vacuum that is going to pull any liquid through to get all of the liquid being removed from our organic solvent. And this is part of our recrystallization process, which I'll talk about in just a second. So the two types of funnels, as we can see, is the Buchner funnel and the Hirsch funnel, and they do have two slightly different shapes. Just be aware that you may be asked to draw one of them, and we should always have it connected into a vacuum pump. So recrystallization is the dissolving of a solid in, very importantly, the minimum amount of a hot solvent that will dissolve the impurities, but not the desired organic product. If we dissolve the desired organic product, that is completely against the point of what we want to do. We want to only be dissolving the impurities. And the steps that we do for recrystallization are as follows, and I would strongly recommend that you memorise these. As I said, they love to ask this in an exam. So how do we do it? Well, we add an impure solid and our chosen solvent, whatever it may be, onto a conical flask, and we heat very close to the boiling temperature of the solvent. And we continue to add just a small amount of the solvent until everything has dissolved. Then we carry out a hot filtration to remove our insoluble solids, using a hot filter funnel, and then we allow the liquid to cool and form crystals of our organic substance. We can then filter it to remove our impurities, and we do that using our Buchner or our Hirsch funnel. And then we wash with ice cold solvent, and then we dry the crystals in a desiccator. So it's very important that we understand that it is the minimum amount of solvent. We don't want to use more than what we have to. And then we allow it to cool in order to form our crystals. So the last thing that we can do to test the purity of a solid, to make sure all of our purification techniques have worked, is we can determine the melting point for a solid, or we can look for the boiling point of a liquid. If we have this, basically the way that we set it up is we use something called a capillary tube, which is basically just a little glass tube that has got a seal at the bottom, and we put our solid into that. We then attach it to a thermometer and we put it into a liquid. As we heat the liquid, that will then cause the solid to heat, and eventually it will get to a point where the solid will melt, and then we just read that off the thermometer, and that is our melting point. Sometimes you may see a piece of apparatus that does this for you, where you just put the capillary in and you turn it on via electricity and a light. It just depends on what equipment you have in your lab. This is a slightly more simple way to do it. If it's a boiling point of a liquid, of course, we just heat it using our Bunsen burner or a hot plate, and then we test it using a thermometer. We test the temperature that it boils at. Once we get either the boiling point or the melting point, we can then compare the values with known values for pure compounds. So we'll have a database of the melting point of any pure organic compound, and we can check how close our value is to it. One major disadvantage, though, is that different organic compounds can sometimes have the same boiling or melting point. So we just need to be aware of that. So that's when we would then move on to do further analysis, such as mass spec, IR, or NMR, because that would show up any impurities in there as well. So let's have a look at a past paper question. We're going to look at June 2017, and this is specifically looking at recrystallization. It's a 5-marker. I did say they'd love to ask this in an exam, so let's have a look through it. So we want to have recrystallization of this impure sample of mandelic acid. Doesn't matter that we've never heard of that before, the steps don't change. And we're going to use methanol as our solvent. So the recrystallization steps are summarised, and they're asking us to provide the purpose of each step, specifically referring to any words in bold. So step 1 is we want to dissolve the sample in the minimum amount of hot ethanol. So why do we want to do this? Well, that's because we don't want to have the sample being too dilute. We want to ensure that we're going to get lots of crystallization, and actually the main reason, the way that we would phrase it, is we want to form a saturated solution. If we have a saturated solution, it means as we cool, crystals will form. Step 2 is then looking at the hot solution being filtered. So of course, why do we want to filter? Well, that's very simple. We want to remove impurities. Why do we want to do it hot? And basically the reason that we do that is so that we have the maximum amount of the mandelic acid remaining in the solution. We don't want any of the mandelic acid to be passed through our filter paper. We want to keep that in the solution. And why do we filter? Well, we filter to remove insoluble impurities. Very important that we know it's for the insoluble impurities, or undissolved, or any solid. Step 3 is then looking to where we cool the filtrate and why we cool it in an ice bath. So that we of course want to cool it in order to crystallize, but why do we cool it in an ice bath? Well, we want to make sure that we're getting the maximum yield, or it allows the maximum amount of solid crystals. Okay, it is not about speeding up the crystallization process. We don't actually want it to speed up. We want it to be a nice slow process, but we use an ice bath in order to make sure that we get all of our product crystallizing, or making sure that we get a maximum yield. And then we filter using suction filtration, and that removes the soluble impurities. Okay, and that's the soluble or the dissolved impurities. So that's the 4 key steps that we have for recrystallization. We can have a look at the mark scheme as well. And it tells us basically what we've just said, that we want to dissolve it in the minimum amount so that we have all of the mandelic acid in our solution. We want to undergo hot filtration so that we keep the maximum amount in solution, but we're removing our insoluble impurities. We put it into the ice bath to allow the maximum yield of crystallization, and we undergo the suction filtration in order to remove any soluble impurities. So that's everything for this video. That is us at the end of topic 20 and therefore at the end of A2 chemistry. It has been a very long journey, and I'm hoping that everything that you've found in this video has been useful. And if you have any questions, please feel free to ask them below. I'd recommend you find some past paper questions on these techniques and give them a try. Of course, you can try the one that we went through in this video if you want to rewind. And hopefully we'll see you back on the channel in future for any other topics that you might want to revise.